Hello everyone, thanks for being interested in our paper. I am Bahar Asgari and I am so excited to present Copernicus, a study that focuses on sparse problems that exist in various application domains. For instance, recommendation systems that create a big portion of execution cycles at data centers, for instance 65% of AI cycles in Facebook's data center are sparse. Scientific computing and graph analytics that create more than 96% of today's supercomputer workloads are sparse too. And in some other cases, such as in neural networks, although initially data is not sparse, but we make them sparse to get rid of storing unnecessary data and unnecessary computation. When matrices are sparse, a common practice is to compress them so that we can store them more efficiently and also reduce data transfer overhead. However, when it comes to processing the compressed matrices, we have to first find out the locations of the non-zero values. This process of decompression, however, can be slow and create a bottleneck. As more and more domain-specific architecture designs are being proposed for efficiently accelerating sparse computation, efficient decompression gains more importance as well. However, despite the key role of decompression mechanism, no study has extensively studied the impact of decompression mechanism on performance when targeting domain-specific architecture designs for sparse problems. To address this gap of knowledge, we propose Copernicus, a study that performs a thorough characterization of performance implications of various compression formats that are frequently used in a wide range of sparse workloads. Copernicus is the first work that studies compression formats from the hardware point of view. Copernicus thoroughly characterizes diverse matrices from various application domains compressed in 7 formats. Copernicus explores the trade-offs between 6 key performance metrics and suggests which parameters must be tuned to achieve desired performance. To do so, it varies key hyperparameters such as partition size to explore their impact on performance. Copernicus also suggests a well-optimized FPGA implementation for decompression mechanisms. In the rest of this presentation, after introducing the experimental setup and the architecture design we use for evaluation, we will be exploring some performance metrics and then we look at some of the trade-offs they make. Our compression formats include frequently used CSR, CSC, blocked CSR, and COO, as well as LIL and L formats that have been used by some recent hardware accelerators, and DIA, which is a format tailored for diagonal sparse matrices. To cover a wide range of sparsity patterns, our workloads include both synthetic and real-world matrices. The synthetic workloads are randomly generated sparse matrices and band matrices. A synthetic random matrix with a higher density represents workloads such as neural networks. We also study real-world sparse matrices from SuiteSparse dataset that are from scientific computing and graph analytics domain, which usually include extremely sparse matrices, sometimes with some structures. To more efficiently process sparse matrices, a common practice is to partition them. We also apply the compression formats only on the non-zero partitions of the main sparse matrices. We repeat all of our experiments for 3 partition sizes. Our other hyperparameters are the density of synthetic random matrices and the width of the band matrices. We perform our study based on an FPGA implementation of a simple streaming-based accelerator for sparse matrix vector multiplication, or SPMV, because it is a kernel that can be found in almost all of the mentioned sparse workloads. The top-level pipeline for processing compressed partitions is shown in this slide that includes 3 stages: memory read, compute, and memory write. The compute stage of the top-level pipeline iteratively creates dense non-zero rows in the decompression stage, which we tailor for each format. And then the next stage of the pipeline applies a dot product between the result of the decompression and the corresponding part of the vector operand of SPMV. For details about each compression format and our well-optimized implementation for each decompression mechanism, please refer to our paper. Let's start evaluating performance by looking at the latency overhead of decompression. In other words, we want to see how decompression impacts the execution time of SPMV. To do so, we use a simple metric called sigma that indicates the time to perform SPMV over the time to perform dense matrix multiplication. The time to perform SPMV would include decompressing the matrix and then performing the dot products, whereas that of dense MV would be performing only the dot products on all the rows of the non-zero partitions. In fact, for the dense format, sigma is 1. The bar chart in this slide shows sigma for SuiteSparse matrices. A sigma smaller than 1 indicates that compression can also help us reduce execution time. As the figure shows, only BCSR and COO can guarantee fast execution for most of the workloads here. A sigma greater than 1, however, indicates that because of decompression, the entire SPMV would be slower than if we were to process all elements of the matrix, even if they are 0. We also want to explore the impact of a few hyperparameters on sigma. To do so, first we increase the density of random sparse matrices as shown in the diagram in the left. As the figure suggests, the decompression overhead of COO, CSR, and CSC dramatically increases with the density. The reason for that is that the decompression mechanism for these three formats cannot be fully parallelized. For instance, for CSR, to retrieve the column indices and values, we do not know in advance which elements of them are going to be accessed. Therefore, we cannot partition and allocate them across different blocks of VRAM to access them in parallel. For more details on limited parallelism, please refer to the pseudocodes of well-optimized implementations in our paper. In addition to limited parallelism, because of the mismatch between the order of compression and the order of computation in our particular hardware, we see that CSC performs the worst. BCSR, however, offers a reasonable execution time for various levels of sparsity because it at least offers interblock parallelism. We also changed the widths of band matrices from 1 to 64 to see the impact on sigma. As the figure in the right suggests, COO, CSR, and CSC can neither tolerate wider band matrices. The reason is still the more number of non-zero elements that must be handled without benefiting from parallelism. Similar to the left figure, BCSR is still a good choice. The decompression of BCSR would be faster than all other formats if the widths of BCSR blocks match the widths of band matrix, which is in this case 4. Therefore, based on these two observations, we see that even though for extremely sparse matrices like those from SuiteSparse dataset, COO offers fast execution, it cannot be the choice for less sparse workloads. So far, we saw that BCSR can perform well in terms of execution time for various matrices. However, that statement for random matrices is true only if the partition size is small. As the figure in this slide shows, when partition size increases, the decompression overhead of BCSR increases dramatically, even though the decompression mechanism can be better parallelized when the partition size increases. The reason is that when partition size is larger, more number of dot products must be done per block, whether a row has any non-zero values or not. Till now, we only explored the performance of computation stage of our top-level pipeline. But in an ideal pipeline, we want both memory read stage and compute stage to perform at a similar speed, so that neither of them become a bottleneck or stay idle and waste the resources. To explore how balanced each implementation is, the three diagrams in this slide show memory latency in y-axis and compute latency in x-axis for SuiteSparse, random, and band matrices. The blue lines illustrate the ideal balance, and the size of the markers reflects the partition size. As the diagrams show, CSR and CSC are always poorly balanced because they only focus on memory optimizations rather than fast computation. On the other hand, we see that BCSR and LIL are fairly balanced for all three types of workloads because they neither over-optimize the storage nor are aggressively tailored for a particular sparsity. Besides, the decompression of both offers reasonable parallelism. For instance, LIL compresses matrices only on one dimension, which causes more memory overhead compared to CSR, but instead it enables parallel computation. The next metric we want to explore is memory bandwidth utilization, which simply reflects the ratio of useful data over all transmitted data that includes metadata as well. Let's review some of our observations here. First, as the figure on the left shows, we vary the widths of the band matrices. As expected, the memory bandwidth utilization of dia for a band matrix with the width of 1, which is basically a diagonal matrix, is almost 1. The slight difference occurs because we still need to save one diagonal number for that main diagonal. Therefore, this memory bandwidth utilization would converge to 1 as partition size grows. In this particular figure, the partition size is 16. However, as we can see, as soon as the width grows to more than one single diagonal, the memory bandwidth utilization of dia drops, although it is still better than most of the other formats, but not BCSR. The reason for BCSR to utilize memory bandwidth better than dia is that it adds only the overhead of one additional coordinate per one partition, whereas dia keeps adding more metadata as the width grows. Therefore, for the same reason that dia converges to full memory bandwidth utilization for widths of 1, BCSR converges to full memory bandwidth utilization as the width of the band matrix increases. We also performed a similar observation for random matrices while increasing the density. As the diagram on the right shows, for a wide range of densities, LIL offers higher memory bandwidth utilization than other formats, although for higher densities it is not as efficient as CSR or CSC, since LIL only compresses the matrix over one dimension rather than both of them. Power consumption is another metric that we must study, especially when we target hardware accelerators with limited power resources. The figures in this slide show only the breakdown of dynamic power consumption of all tailored pipelines for logic, VRAM, and signals, among which the latter dominates the total dynamic power consumption. The figures also illustrate power consumption for various partition sizes. For the numbers of static power consumption, please refer to our paper. Let's review some of the insights that these figures can suggest together with some of the prior observations that we made. First of all, as we see, not only does COO consume the least dynamic power consumption, But also, as we saw earlier, it is the fastest in terms of execution time for SuiteSparse matrices. We can also observe that if achieving lower power consumption and high throughput would be a goal, BCSR is a better choice than COO. For band matrices, we see that ELL performs well in terms of latency and throughput, while as we see here, it also consumes less power compared to LIL, which can offer similar speed, but at a higher power consumption. Now that we explored the performance of decompression in terms of various metrics, let's put our observation together to see what we learned. The figure in this slide puts together all 6 metrics for SuiteSparse workloads. In this figure, 0 means worst and 1 means the best. For details about throughput and FPGA resource utilization that we didn't cover in this presentation, please refer to our paper. The first thing we learned from this study is that although in scientific computing and graph analytics, the common pattern of sparse matrices are semi-diagonal, in fact, a non-specialized format such as COO performs more quickly and better utilizes memory bandwidth compared to a specialized format such as dia. This is because of the compatibility of a more generic format with a generic hardware for a common computation such as SPMV. In addition, a generic format better tolerates the variations in the distribution of non-zero entries. If power consumption and FPGA resource utilization must also be optimized, then LIL or BCSR are other appropriate candidates. We also draw a similar figure for band matrices. Today we saw that for particular band matrices, a pattern-specific format such as dia can near perfectly utilize memory bandwidth and can do it better as the partition size increases. However, to allow such utilization to effectively impact all performance metrics, the computation engine must also be tailored to the format. Otherwise, the mismatch would create a computation bottleneck. From Copernicus, we also learned that the memory bandwidth is not always the performance bottleneck when targeting sparse problems. Therefore, the performance of sparse problems cannot always be improved by simply adding more memory bandwidth to the system. Copernicus also showed that when using a format such as CSR to efficiently use storage, since the computation will potentially create a bottleneck, we won't need to use a high bandwidth, high cost memory. Or if we do have such a memory and if we have to use CSR, then the implementation of the computation must be further optimized. Last but not least, we learned that for less sparse workloads, such as neural networks, optimizations beyond simple partitioning of size 8x8 or at most 16x16 would hurt performance, although it might help reducing the memory footprint. Extracting the non-zero partitions from the neural networks can be done with the aid of structured pruning techniques. Thanks for watching my presentation. I'd be glad to answer your questions in the Q&A of session 1 on Monday, November 8th at 10 a.m. Eastern Time.